Hello, my name is Shannon McGivney, and it is a nice, warm, hot, sunny day in Bend, Oregon, and I'm excited to share with you my Case Connections Unit 2 discussions. We're going to talk about glucose update in 4 different healthy cell varieties, and then we're going to cross-compare that with cancer cells and see how cancer cells can continue to multiply at the speed and rate that they do. Let's first talk about liver tissue. It's a scrappy one, which is why I want to begin there. It really helps you leverage your body for homeostasis as it relates to blood glucose. During the fed state, the liver converts glucose into glycogen, which is easily stored locally in the liver. It's kind of like feast or famine, right? After a fed state, the liver will actually take that free glucose that's just cruising through your blood and will store it for a rainy day. During fasted states, like what I'm in right now, pre-lunch and breakfast, my body is actually being run on the transfer of glycogen back into glucose to feed my cells and my brain, so I keep going. You have a steady stream of blood glucose level. And in a prolonged fasted state, your liver pulls out all the stops. It sources its hepatic glyconeogenesis, where it can actually convert amino acids, pyruvate, fats, and waste, and use all of those to build glucose through that process mentioned. Now let's talk about your muscle tissue, specifically your skeletal muscle tissue. As we mentioned before in the liver, glycogen is very rapidly depleted, and that's our first source of energy in skeletal muscle. It's actually located in the muscle itself. It's intramuscular glycogen. After that's depleted, your body moves to blood glucose in order to source energy. And it does that through 2 main hacks. It's got a surface membrane glucose transporter, often the GLUT4 when we're talking about striated muscle tissue. And then it also utilizes intracellular substrate flux. So these are 2 hacks that skeletal muscle has that the other tissues don't have. You'll notice a lot of pre-exercise drinks and even post-recovery drinks will leverage the second option here. We have amino acid L-arginine, and that basically helps your nitrous oxide production, which causes vasodilation. It makes your blood vessels bigger. What that does is that helps cellular respiration, and it helps bring all the nutrition in and waste out. To facilitate both of these hacks. So the other one that I'd like to mention is creatine. I don't know if you remember when that was illegal. Was it Barry Bonds playing baseball? Some home run slugger caused quite a controversy with creatine, because what it does is it actually allows your muscles to swell and hold and retain more fluid, which allows these hacks to work better and longer, which decreases your recovery time so they can train longer and harder and have more productive muscle reconstruction. Now the brain. The brain wants glucose all day long, every day, all day. And it utilizes 2 main hacks in order to do so. First, it utilizes GLUT1 as a transporter to transfer the glucose from the blood into the brain. Also, the brain capillary endothelial cells unlocks the glucose from the blood-brain barrier. These endothelial cells are unique in the way they're structured in such a way that glucose can transfer freely across that barrier. In an emergency, the brain will also source ketones as a form of energy to break down. This is not the brain's first choice, but in a famine state or a very prolonged fast state, the brain will switch to this. This is part of the reason when people are on the keto diet, the ketogenic diet, they have what's called the flu, the keto flu, for approximately anywhere from 1 week to a month. And that's your brain adapting to switching from typical glucose sourced from red blood cells to and sourced from that GLUT1 uptake, like I was mentioning and they saw in the diagram, to using ketones and breaking those down for glucose for energy. Now we're going to talk about adipose tissue. Adipose tissue has had a bad rap in most of medicine, and it's been largely ignored as just a storage bin that no one wants to look at, and something that's off-putting to pretty much everyone, because no one wants more fat on their body. So I'd like to talk about basically how it's actually a really high-performing form of energy. Adipocytes, adipose cells, adipocytes release fatty acids into the bloodstream, and they do so in a fasted state. And if you recall, those fatty acids are quite helpful when sourcing energy for skeletal muscle during exercise, because that glycogen is quickly depleted. These fatty acids is a great form of ancillary energy for muscles. It's also used by just about all of your organs. So once again, it is a very wonderful source of energy. It's very efficient. It results in more energy per unit of mass than carbs can even create. And that's what we're eating. It's just very interesting because what you're taught growing up is carbs the form of energy. And this is once again why that ketosis or ketogenic diet is so popular, because they're sourcing fatty acids for their energy. And then it's also 2 times the energy production of glycogen. So once again, much, much more efficient. Now, when you're not in a fasted state, it is primarily a storage mechanism. So you can see on your body in any type of area where you store fats, that can be because you have an excess in caloric intake. It can also be because you have hormonal irregularities or imbalances that need to be adjusted, because once again, your pituitary is telling all of your other hormones when and how to start and stop. And that includes insulin, and insulin is key in the storage of glucose here in adipose tissue. So actually, insulin is one of the hormone regulators that tells glucose to go ahead and be stored glucose. And it does that through the transporter protein GLUT4. And it tells the glucose to store in adipose tissue by creating adipose tissue or skeletal muscle as well. Those are the 2 main mechanisms. Cancer cells have evolved in such a way that they guarantee they are fed. They've come up with 3 new strategies in addition to the ones mentioned before in the previous 4 tissues. They actually bypass the mitochondria in strategy number 1. It's called the Warburg effect. And basically what they do is aerobic glycolysis, and they do it outside of the mitochondria. So this completely bypasses. Very, very quick and efficient. In addition to that, they also have strategy number 2, which is oxidative phosphorylation. You'll see on your graph right here, that is denoted in red. Strategy number 1 was in blue. And you can see your mitochondria is that brown loop there, and that is involved in strategy number 3, which is mitochondrial uncoupling. Now, if I show you this next graph, it shows you additional pathways for some of the chemistry that's involved in these 3 strategies. Cancer cells alter the metabolism in order to increase glucose uptake and the fermentation of glucose to lactate. That is what we call the Warburg effect. The next case we're going to discuss is case number 3. And in this case, we have a young patient who has very, very low blood serum levels of insulin. And when that happens, even after a fed state, the insulin is still significantly low. That's going to result in a lot of free-flowing glucose in the blood, because insulin is supposed to come out after you've had a large meal and you are now in the fed state, and all that free-flowing glucose needs to leave the bloodstream because now it's too high, and it needs to feed the cells and organs and the rest of your body to maintain homeostasis. In the fast state, then glucagon is released from the liver and increases blood glucose levels. But in this instance, in case 3, the serum levels are showing that insulin is not doing its job on that teeter-totter, insulin and glucagon. So what's going to happen is it's going to result in a large or high level of blood glucose, because insulin is like a key unlocking the cells for blood glucose, which then relieves some of that level in the blood and basically disperses it through the cells. So that's what I would expect in that patient. Other hormones involved are going to be, I mentioned glucagon, insulin, cortisol, and adenosine. Two regulatory enzymes that are also going to be playing a key role here, trying to decrease the amount of glucose, is GK and PFK, so glucokinase and phosphoruticanase, and those are also part of breaking down glucose in glycolysis.